Welcome back to TalkTensors. Today we're taking a deep dive into this paper called Encoding Argumentation Frameworks to Propositional Logic Systems. And this one really kind of caught our eye because it's blending this world of arguments with like the really precise world of logic.
Yeah, it's a really cool approach. Because it's tackling this question of, how can we analyze arguments rigorously?
Yeah.
Like think about, it's like a courtroom where you've got lawyers presenting their arguments and they're trying to like poke holes in each other's cases, right? And so this paper gives us this way to kind of translate that whole back and forth into the language of logic, right? So we can actually use these like powerful logical tools to figure out, like which arguments really hold water.
It's not just about who's like shouting the loudest or who's the most charismatic. It's about the actual, like the structure of the arguments themselves.
Yeah, exactly, yeah. The paper really zeroes in on these things called argumentation frameworks, which are basically like maps of a debate, They show us who's arguing what and, who's disagreeing with whom. But logic gives us these tools to go beyond just like mapping it out, right? It lets us actually reason about those arguments. Right. So we can figure out, which ones are the strongest or which ones lead to the most logically sound outcome.
Okay, I'm definitely intrigued. But how do we go from like this messy, back and forth of a debate to something that a computer can actually like understand and work with?
That's where this whole idea of encoding comes in, right? The paper looks at different ways to basically translate these argumentation frameworks into different systems of propositional logic. So it's kind of like we're converting a real world debate into this series of like, logical statements, almost like a code, For example, imagine we're arguing about something like climate change, right? This paper gives us this framework to map out all the arguments, the counter arguments, all of that. And then we can use logic to figure out which side actually has the strongest case overall.
So instead of just having this jumble of opinions, we can turn those arguments into something like a mathematical equation, right? Something that we can actually solve.
Yeah, that's the idea. And the really neat thing is that different types of logic can capture different aspects of arguments. So the paper explores this, the classic true or false logic, but it also looks at systems that can handle uncertainty, like saying, well, this argument is maybe partially true. They even get into fuzzy logic, which allows for these like degrees of truth, right? So it's like saying this argument is maybe like 80% likely to be valid.
That's really interesting. I can see how that would be super useful in real world debates, where things are rarely just black and white. But before we get too deep into the technical details, I think it might be helpful to give our listeners a little bit of historical context, right? Like what were the key developments that kind of paved the way for this research?
Yeah, so the groundwork was really laid by this guy, Dung, right? He did this really important work on argumentation frameworks back in 1995. He basically provided this like basic framework for how we can actually represent arguments and how they relate to each other. It's almost like he created a game board, complete with the pieces and the rules of engagement. That's kind of what he did for argumentation.
So Dung set the stage, and then other researchers kind of came along and started developing the actual strategies for playing the game.
Exactly, yeah. Researchers like Besnard and Dutre, they were some of the pioneers in connecting argumentation frameworks to logic. They developed these early encoding techniques using classic true or false logic. And that laid the foundation for the more like generalized approach that we see in this paper that we're talking about today.
Okay, so this paper is building on some pretty significant work for sure. But what are some of its truly unique contributions? Like what makes it really stand out from the crowd?
Well, I'd say one of the key insights is how they use these multiple encoding functions to show us the connection between, the world of arguments and the world of logic. And they show how these encodings let us actually translate this problem of solving an argumentation framework, like finding the set of arguments that kind of win the debate, so to speak. And they show how we can actually translate that into a problem that can be solved using logic.
That's fascinating. So we can basically use logic to like identify the winning arguments in a debate, right? Like, it's almost like they found this like Rosetta Stone for translating between the language of arguments and the language of logic.
Yeah, exactly. And what's even cooler is that they don't just stick with this basic true or false logic, right? They also explore how these encodings can be used with systems that allow for these degrees of truth, like we talked about before with fuzzy logic.
So instead of just saying, okay, this argument wins, we could actually say something like, this argument has a strength of like 0.75 or something like that.
Exactly, yeah. And that really allows us to capture the nuances of real-world arguments, where things aren't always just black and white, right? And this guy Gabay did some important work on equational semantics, which basically lets us assign these numerical values to arguments. And actually fits in really well here. This paper shows how those equational systems can actually be derived through the encoding process itself.
Wow, this is getting me really excited. It feels like we're moving towards a much more sophisticated way of understanding how arguments actually work, and that has like huge implications for all sorts of things like AI development and even just understanding human reasoning itself. But before we dive too deep into those implications, let's take a quick pause. And when we come back, we'll unpack some of the specific encoding techniques that are described in the paper, and we'll see how they actually play out in practice.
Welcome back to TalkTensors. So before we went to a break, we were talking about how this paper uses encoding to bridge the gap between argumentation frameworks and logic. And now let's actually kind of delve into the nuts and bolts of how these encodings actually work.
Okay, yeah, I'm ready to roll up my sleeves and get a little bit more technical. So the paper talks about several different encoding functions, right? Each one with its own, strengths and weaknesses. Can you maybe walk us through some of the key ones and explain how they're different from each other?
Absolutely. So one of the most fundamental encoding functions is what they call the elementary encoding, right? And it's basically like a super basic translation that really just focuses on the attack relationships in an argumentation framework. So imagine you've got this debate where, one person's argument directly contradicts another person's argument. The elementary encoding basically captures that conflict by saying, okay, if this argument is accepted, then the argument that it's attacking can't be accepted.
So if argument A attacks argument B, we would encode that as if A is true, then B is false.
Right.
Is that kind of the idea?
Yeah, that's the gist of it. And by linking all these statements together, we can create this formula that represent the entire structure of the argumentation framework, right? So it basically shows us all the points of conflict, almost like a map highlighting all the battlegrounds in a war, so to speak.
So the elementary encoding is like a blueprint of the debate, showing us where the disagreements lie. But does it actually tell us which arguments win, so to speak?
Well, not exactly. It just shows us which arguments can't coexist at the same time. To actually get closer to figuring out the winning arguments, we need to use more sophisticated encodings, like the normal encoding or the regular encoding.
Okay, those sound intriguing. What makes them different from that elementary encoding that we were just talking about?
So the normal encoding kind of takes things a step further, right? It creates this stricter rule for when an argument can be accepted. So think of it like, a jury verdict, right? For a guilty verdict, you need all the jurors to agree. Similarly, for an argument to be accepted in the normal encoding, all of its attackers need to be rejected.
So if argument A is being attacked by, say, arguments B and C, then A can only be accepted if both B and C are rejected. Is that right?
Exactly, yeah. And this type of encoding is really useful when we're dealing with something called stable semantics, which basically means we're trying to find a set of arguments that can defend themselves against any attacks that are coming from outside of that set.
So it's like a fortress where every argument inside is protected from outside attacks. Gotcha. That makes sense. But you also mentioned another encoding, the regular encoding. That one sounds even more complex. How did that one work?
Yeah, you're right. The regular encoding is a bit more involved. It's based on something called admissible semantics, which means that for an argument to be accepted, it needs to be defended against all of its attackers. However, the regular encoding adds this extra layer, right? It says that an argument can only be accepted if it's being defended by other arguments that are also accepted. It's kind of like, needing references to get a job, right?
So an argument can't just fend for itself. It needs support from its allies, so to speak. That seems like it would lead to some pretty interesting dynamics, especially in a complex debate with lots of interconnected arguments.
Absolutely. And that's what makes the regular encoding so powerful. It lets us actually capture those complex relationships between arguments and identify these sets of arguments that are both admissible, meaning they can defend themselves, and complete, meaning they can defend each other.
Okay, my brain is starting to get a little overloaded here with all these, logical operators and conditions. Could you maybe give us a concrete example of how these encodings would actually play out in a really simple argumentation framework? Maybe that would help solidify things for me.
Yeah, sure. Let's consider just a very basic scenario, right? Let's say we have three arguments, A, B, and C, where A attacks B and B attacks C. So it's like this chain reaction where each argument is trying to take down the one before it.
Okay, so it's like dominoes falling, right?
Yeah.
A pushes over B, B pushes over C. I can visualize that.
Okay, yeah. So let's see how the elementary encoding would represent this little chain here. For the attack from A to B, we would have the statement, if A is true, then B is false. And for the attack from B to C, we would have, if B is true, then C is false. Pretty simple and straightforward, right?
Yeah, that makes sense. It's basically just directly translating those attack relationships into these like basic logical statements. What about the normal encoding? How would that work in this domino scenario?
All right, so now with the normal encoding, we start to see some more definitive statements about which arguments could be accepted or rejected. So for argument A, which doesn't have any attacker in our scenario, the encoding would simply say A is true.
Right, because nothing is challenging A, it gets to stand unopposed.
Exactly. Now, for argument B, which is being attacked by A, the normal encoding gets a bit more interesting, right? It says B is true if and only if A is false. Remember, under the normal encoding, an argument can only be accepted if all of its attackers are rejected.
So B can only stand a chance if A is taken out of the picture. Okay, I see how that's stricter than the elementary encoding. What about argument C then?
Well, argument C is being attacked by B, so its normal encoding would be C is true if and only if B is false. Again, it can only be accepted if its attacker, B in this case, is rejected.
Okay, starting to see the pattern here. The normal encoding really lays down the law, making it clear which arguments can and cannot coexist. But what about the regular encoding? How does that handle this little chain of attacks that we've got going on here?
So now, the regular encoding adds that extra layer of needing support from other accepted arguments.
Right.
Argument A, with no attackers, still kind of gets a free pass. It's still A is true. But for B, things get a little bit more complicated. Since B is being attacked by A, and it doesn't have any other arguments defending it, its regular encoding becomes B is true if and only if A is false and B is defended.
Ah, that's where that recursion element comes in, right? B needs a friend to back it up, but in this case, it's all alone. What about argument C? Does it have any allies in this debate?
Actually, yeah, it does. So C is being attacked by B, but it's potentially defended by A since A is attacking B. It's like this strange triangle, of alliances and rivalries. So C's regular encoding becomes C is true if and only if B is false. And either C is defended or A is true.
Wow, that's quite a mouthful. But I can see how it captures those more intricate dependencies between the arguments, right? It's not just about who attacks whom. It's about this whole network of support and opposition.
Exactly. These encodings, they're not just some, abstract formulas. They actually represent the strategic landscape of the debate. And by applying different types of logic to these encoded formulas, we can start to analyze these arguments in a much deeper way. We can identify the sets of arguments that are most likely to win, so to speak, based on different criteria. We can even start to explore the strategic dynamics of how arguments attack and defend each other, which is really cool.
Yeah, this is really mind-blowing stuff. It feels like we're deciphering the code of argumentation itself, using the precision of logic to unravel these complexities of human debate. This is really fascinating. All right, and we're back for the final part of our TalkTensors deep dive into encoding argumentation frameworks. We've been talking about how this paper takes this kind of messy world of arguments and translates it into this super precise language of logic. And it's really kind of opened my eyes to how we can use logic to analyze and understand debates in a whole new way.
Yeah, it's definitely a game changer. And honestly, we've only just scratched the surface of what's possible here, One of the things that I think is really exciting about this paper is how it explores this idea of fuzzy logic, which lets us capture those nuances of real-world arguments where things aren't always just true or false.
Yeah, you mentioned fuzzy logic earlier, and I'm really curious to hear more about it. How does it actually work in the context of these encodings?
So fuzzy logic basically lets us assign these degrees of truth to arguments, right? So instead of just saying, okay, this argument is true or this argument is false, we can say something like, well, this argument is maybe 60% likely to be true, or this attack is stronger than that attack, and just gives us a much more realistic way to model real-world debates where the evidence can be ambiguous and, arguments can have these varying levels of persuasiveness.
So instead of having this binary win or lose situation, we can actually rank arguments on a spectrum based on their strength. That seems incredibly useful, especially when you're analyzing these complex debates with lots of moving parts.
Absolutely. And what's really cool is that this paper shows how these degrees of truth can be incorporated directly into the encoding process itself, right? So by choosing specific fuzzy logic operations, we can create encodings that actually capture the subtleties of different argumentation scenarios.
So it's kind of like we're fine-tuning the encodings to match the specific rules of the game, so to speak, right? Whether it's like a legal debate, a political discussion, or even a scientific argument.
Exactly. That flexibility is really one of the most powerful aspects of this research. It basically provides us with this framework for building these like custom-tailored models that reflect the nuances of all these different argumentation domains.
And this brings us to some of the potential applications of this research, which are honestly like mind-blowing. Imagine being able to build AI systems that can not only understand arguments, but can actually like participate in debates, crafting persuasive arguments and strategically deploying them to try to influence the outcome.
Yeah, that's a vision that a lot of researchers are working towards. Imagine like an AI lawyer, right? That can sift through mountains of legal documents and identify the strongest arguments for their client's case, and even anticipate the counter arguments from the opposing side. I mean, that would completely revolutionize the legal profession.
Or what about like an AI diplomat?
Right.
Trained on these massive data sets of historical negotiations and treaties, and they can navigate these super complex geopolitical situations by like crafting persuasive arguments and finding these mutually acceptable solutions through like reasoned dialogue. I mean, the possibilities are truly endless.
And this research is laying the groundwork for that future, By connecting the world of argumentation to the rigor of logic, it gives us the tools to build this next generation of AI systems that can actually reason, debate, and maybe even persuade.
It's both exciting and a little bit daunting, to be honest, to think about the implications of this technology. Like, if we can actually teach machines to argue effectively, what does that mean for, the future of decision-making, conflict resolution, and even just the nature of human discourse itself?
Yeah, those are really important questions that we need to be asking ourselves right now. As AI systems become more and more sophisticated in their ability to process and generate language, we need to make sure that they're grounded in these principles of like sound argumentation, right? We don't want AI systems that are just good at winning arguments. We want AI systems that can engage in debates fairly, transparently, and ethically.
This deep dive has been an incredible journey, and honestly, I'm left with this sense of awe at the potential of this research. It's clear that, encoding argumentation frameworks into logic is still kind of in its early stages, but the implications are massive. It has the power to transform not only how we build AI systems, but also how we understand ourselves and how we interact with the world through, arguments and debates.
It's a field that's just bursting with possibilities and challenges, and it's one that's definitely going to shape the future of AI and its impact on society. I can't wait to see what groundbreaking discoveries come out of this area of research.
Well, that's a wrap for this episode of TalkTensors. We encourage you to check out the paper for yourself and kind of dig a little deeper into this fascinating topic. The link will be in the show notes. Until next time, keep those tensors firing and never stop exploring this amazing world of machine learning.